what? Period. Now, at this junction, it is the value of your period you now use to obtain. They said we are told to calculate our period, so period is out there. You punch your calculator. Now, for the angular velocity is we have something like this. Your normal velocity as omega r. Are we seeing it? Now, we have 240 revolution per minute. 240 rev per minute. Are you seeing it? This rev per minute signifies velocity. So you just insert 240 here. Here you get. Now this is our angular, then our what? Radius as 2. So by the time you look for, you now have your 240 divided by 2, which will give you 120. Now this one will now give you what? Meter. Since it's angular, it's radians per second. Are we seeing it? So that is how you obtain all that. So without wasting much of our time, let's go to number 2. Number 2 says that what's the angular speed if a body whose frequency is that? Now, the frequency is 50 Hz. The third question, okay, that question still goes with the first question, which has already been solved. The third question says, distinguish between damped and forced vibration, which we have already analyzed. So, Newton's law of motion. We have a German scientist known as Galileo initiated the dynamics, and after his death, the work was continued by Sir Isaac Newton. So, if you are being asked that the main scientist that initiated this gesture, normal Newton's law of motion, you know, the name is actually being named after Newton, but the actual person that initiated the law of motion is what we call Galileo. It initiated the dynamics, and after his death, then Sir Isaac Newton now took over. Now, among other things, Newton propounded basic laws of motion, which are still very much valid to date. Now, let's start. Newton's first law of motion. This law says that a body will continue to be in a present state of rest, or in its motion, or if it's in motion, it will continue to move with uniform speed in a straight line unless an external force is being acted on it. Let me put it down in another way. You have this body here. Let's say this is a pen. This pen is on this table. Are we getting it? In a very good room. Now, if this pen is not being affected by any external force, nothing touches this pen, and this room remains locked for 50 years, that pen will be at that point. It's not going to move. That's what the law is actually trying to tell us. It's in two ways. The first case, static. The second state, on motion. Are we getting it? Now, on the first case now, if this body is not being exerted, or is not experiencing external force, nothing is touching it, no breeze is touching it, it's just static there. For 50 years, it's going to remain that way. Why, when the ball is in motion, let's say a ball now is in motion, if this ball is not, when you kick your ball now, kick it towards a particular a forward direction. Now that ball will continue to move. Now what brings the ball to a stop, if I will ask? Two things. Number one, the topography, location, or the ground structure of this ball at which this ball is moving. If the ground structure is chaos, that is, the ground structure is not smooth, all these forces, they tend to reduce the speed at which this ball, you understand, usually starts with, let's say it started with 50 meters per second. By the time it gets to this point, the speed will be reducing gradually till to stop. That's force one. Another force that might tend to stop it is what? Wind or breeze. There will be an upward breeze that will be blowing. So these are two forces that tend to what? Bring this ball to rest. But what Isaac Newton now is trying to tell you is that if the ground is smooth, no external force from the ground, no external force from the breeze, this ball will continue to move to infinity. Are we getting it? So those are the two cases stated in Newton's first law. Let me state it again. It states that a body will continue to be in its present state of rest, or if it's in motion, will continue to move with a uniform speed in a straight line unless it is being acted upon by a force. Now, a body being in a constant state of rest or in motion is said to be in a state of what? Inertia. Get that straight. If your body is at rest or is in motion, it's what we call state of what? Inertia. Are we getting it? So those two words needs to be known. Now it is very important to know that once a body is moving in a straight line, it needs no force to keep it in motion, provided there is no external opposing or accelerating force. I already explained it the other time. The body can be moving constantly without stopping if the ground is smooth, no application of force, from the breeze towards that ball. Nothing. Those two factors, if they are not there, this ball will continue to move. So those are the two things that will bring an object to a stop when in motion. But also when it has stayed, if nothing is being touching the object, no external force, nobody is touching it, no breeze, it will remain there static. So that is the analysis of Newton's first law. Now let's go to what we call momentum. It is just the product of mass and velocity. The product of mass times velocity. That is, momentum is defined as the product of the mass and what? Velocity. That is, when you have your Bm as your momentum, then mass times velocity. And the SI unit is given as what? Kilogram meter per second. How did you get that? Kilogram is for mass, meter per second is for what? Velocity. That's the SI unit for what? Momentum. So let's take a look at these 2 points. Look at these two analysis. A bullet of mass 0.05 kg with velocity of 5,000 meters per second and a heavy mass of 2,500 kg. Let me draw it. This is a bullet. Let's say a bullet is of that structure. Then the mass of this bullet is 0.05 kg. It's now moving at a very big speed of 50,000 meters per second. There's also another word, heavy mass, heavy body. The body is very big. Now it has 2,500 kg. That's equivalent to 2.5 tons. How did I know that? 1 ton is 1,000 kg. Hope you know that. So it's 2.5 ton, very heavy. It now possesses a velocity of 1 meter per second. What are we trying to say? We have the same momentum, meaning that if I'm to calculate the momentum of these two, that's this mass times this velocity, and this mass times this velocity, both will have the same value of momentum. That's just the analysis. Now the second one says that the greater the momentum of the bullet, the deadlier it is. You have a bullet, you have someone that shoots a gun. The bigger the momentum of this bullet, the deadlier the bullet. Hope you are getting it. So that is just under momentum. We will expatiate on it as we proceed. Under our Newton's second law, we have the rate of change or movement of a body is directly proportional to the applied force and takes place in the direction of what? Force. That is your F. The rate of change or momentum of a body is directly proportional to the what? Applied force, which takes place in the direction of what? Force. It's given as your what? F directly proportional as what? Mass into V minus T. Are you seeing this? So this is the equation of the what? Second law of motion. So from here you have your Ft equals to what? M into V over U. Are you seeing it? Now this your Ft is what we call your what? Impulse. Is what we call the impulse. So what is impulse now? Impulse is the product of force times what? Time. Force in Newton, time in what? Seconds. So the SI unit is what? Newton seconds. From here now, this is our what? Value for what? This is our mathematical expression for what? Newton's second law. That's the derivation of the equation there. Now, for the third law now, what does Newton's third law say? It says to every action, there is equal and opposite reaction. Take for instance, when we place an object on a table, there will be a reaction on the table. You understand? Of the table on the object. Now the vertical force exerted by the table on the object is equal and opposite to the action of the body on the table. Are we getting it now? For every object, I try to place my table here. I put some object on it. Now those objects are acting. Do you understand? They are acting on that table, which is automatically acting on the ground. But the ground too is now having a reverse. You understand? They are having a reverse action. You understand? They're having a reverse reaction of force from the ground towards that table, which now automatically comes towards the object. That's why that law says that to every action there is equal and opposite reaction. So that is that. Now let's go to laws of conservation of momentum. This law states that in an isolated system, the total momentum of the colliding body remains constant. What do I mean? Two things are involved. You have body A, M1, body B, M2. Are we getting it? So from here now, can I say this body A starts with an initial velocity of u1. This is before collision. This one too is before collision. You know, we have what we call collision. U2, U1. Are we getting it? So now, if these two bodies tend to come towards each other, they want to collide. This is my M1, this is my M2. They are moving towards each other with initial velocity U1. So before collision now, momentum before collision is going to be M1 U1 plus M2 U2. So this particular equation will now equal to momentum after collision M1 V1 plus what? M2 V2. How did we get this? Because we know that if these two bodies are coming together to collide, now when they start their movement, they are undergoing initial velocity. That's the U1. They both have U1. Now when they eventually now collide, they now have V1, V2. V1 for what? The first body, and V2 for the second body. Hope you are getting it now. So at this case now, we'll be able to establish